This is the continuation of Chapter 1.1 through 1.3 for Precalc. Today we're going to be talking about piecewise functions. A piecewise function is any function that behaves differently based on the input value. Okay, for example, f of x is equal to x squared if x less than 2, 6 if x actually equals 2, and 10 minus x in the region greater than 2 and less than or equal to 6. Looking at what that looks like as a graph, we have the picture on the right. As you can see, it's like three different things, including that one little dot at y equals 6. Okay, on our calculators, we would graph this in the following function. Okay, so pulling up the simulator, here we are. Okay, let's clear what we have here. Yep, clear that, and clear that. Okay, so if we go to here, okay, we'll clear that one as well. Okay. So going to here, this picture, okay, we're going to graph y is equal to parentheses x squared, curly brackets x less than 2. So parentheses x squared, oops, not that, squared, close parenthesis, and then curly bracket, which is under second parenthesis, x less than 2. The less than functions are under second math or a second test. Okay, and in this case I want the less than function, or 5. Okay, less than 2, close curly bracket. Now I put the next one, which is x is equal to 6. F of x equals 6 when, second curly, when is that? When x equals 2. Okay, again, second test to find the equal sign. It's not the enter sign. Equals 2. Second curly to close it. And then the last function, which is 10 minus x, I believe it was. Yep, 10 minus x. 10 minus, oh, come on, sorry. Minus x when x is greater than 2. Whoops, not that one. Second test. Greater than is that. The and function, okay, because it's x greater than 2 and x less than or equal to 6. And to do that, I still go to second test, but I have to arrow over to the logic choices and choose and in this case. In this case, x second test less than or equal to 6. Close curly. And let's set the standard zoom window, 6, and we have the same picture. You can't quite see the dot, but it's the same picture. Okay, so we can access the inequality signs and the logic ands and ors under the second test menu. Okay, we use the curly brackets to indicate the test regions. Okay, how are we limiting our domain? Okay, so that's how we graph piecewise functions. Okay, our calculators can do that just as well as graphing our regular functions. Okay, absolute value is nothing more than a piecewise function when the value inside is greater than 0 and the value inside is less than 0. Okay, but our calculators can do that pretty much off the bat because we have the absolute value function under the math keyword. Okay, so going over here, if I want to graph something, let's say I wanted to graph something as an absolute value, I could hit math, move over to the number, and the first one is absolute value. So I could say absolute value of x, and I'll ask it to graph that. I'll disable the first graph. Okay, and if I graph that, that's the graph of the absolute value of x. Okay, so I can do that. Okay, but absolute value functions are also piecewise functions. Okay, so if I have the function y equals x plus 3, absolute value, okay, then y will equal x plus 3 whenever x plus 3 is greater than or equal to 0. If x plus 3 happens to be less than 0, then I have the function minus x plus 3, quantity x plus 3. Okay, the minus basically changes the sign. Yes, it's less than 0, but let's just make it positive. Simplifying the inequalities, I would basically have this, okay? Simplifying them, I would have from x greater than or equal to minus 3, I graph x plus 3. And from minus less than minus 3, I graph minus x plus 3. Okay, so that's how we can graph of an absolute value as a piecewise, in a piecewise format. Okay, it does get more complicated, so let's take a look at this situation. Okay, f of x is two absolute value functions, x minus 5 minus x plus 3. Both of those are absolute values. And both of them I need to set when x minus 5 is greater than 0 or less than 0, and when x plus 3 is greater than 0 and less than 0. So let's do that on a number line basis. Okay, first off, let's look at x minus 5. Okay, x minus 5 is going to be positive whenever x is going to be greater than 0, greater than 5, sorry. Okay, and then it's going to be, let's choose orange, less than 5, it's going to be negative. Okay, x plus 3 on the other hand is going to be positive whenever x is greater than or equal to minus 3. So let's choose another color. How about green for that? So starting at plus 3, it's going to be positive. And on the other direction, it's going to be negative. Whenever x is less than minus 3, it's going to be negative. So let's choose purple for that. Okay. And so that's going to be negative. And that sets our three ranges, because in that area where they overlap, when the green line is positive and the yellow line is negative, that's the section that's going to be the overlap section, from greater than or equal to minus 3 to less than 5. Okay, and I do the same process, okay? Whenever x is greater than or equal to 5, both functions are positive and I can leave them alone. So I have just x minus 5 here and x plus 3 here. In that region between, okay, between x equal to minus 3 and 5, I would basically have to make the first function negative, so that's why I have a minus sign here in front. And I leave the second function alone because that one's positive. Less than minus 3, they're going to both be negative. So I make a minus sign here and I change the sign here from minus to plus. Simplifying all of this, I end up with this set of functions. Okay? So that's how we can graph something with more complex. We still have to treat each absolute value as, is this going to be plus or minus? Is the other one going to be plus or minus? Is there an overlap region? Okay? So, moving on to the last thing I want to cover in this unit, and that's the difference quotient. Okay. Whoops. The difference quotient is this formula that says f of x plus h minus f of x divided by h. Okay. This is something that we can do to calculate the rate of change of a function f of x. So here we have f of x. Okay. I don't know what it is. It's an arbitrary function. And if I want to know how quickly is it changing from f of x to f of x plus h, I can basically choose those two dots on my curve and draw a straight line between them. That line is called the secant line. And it basically helps me to calculate the rate of change of the function f of x between those 2 points. Okay, and so the difference quotient now is basically saying nothing more than the slope of that secant line. Okay, because f of x plus h minus f of x is delta y, and h is nothing more than delta x, rise over run, delta y over delta x. We'll talk more about slope in the next set of videos. Okay, so let's take a look at an example. Okay, if I have my function f of x is equal to minus 2x squared plus x plus 5. F of x plus h becomes this, where I substitute x plus h in parentheses for everywhere I saw x in f of x. So by doing that, I end up with this function minus 2 times x plus h squared plus x plus h plus 5. And after distributing out, I end up with this minus 2x squared minus 4xh plus 2h squared plus x plus h plus 5. Yes, it's a very complicated looking thing. Okay, but the magic of the difference quotient makes a lot of this disappear, because when I actually do it, f of x plus h minus f of x, a lot of things start to cancel out. Okay, in particular, I have the plus 5 here and the minus plus 5 here. That cancels. I have a minus 2x squared and the minus 2x squared. That cancels. Okay, I have this plus x here and the minus plus x here. So everything in the f of x disappeared. Okay, and I'm left with just this minus 4xh plus 2h squared plus h over h. Okay, simplifying that even further, I end up with just minus 4x plus 2h plus 1. So something that started out looking as complicated as it did became fairly easy after simplification. Okay, and so this tells me that the slope of my line, or between f of x and f of x plus h, is this function minus 4x plus 2h plus 1. Okay, and in fact, as we'll find out next year in calculus, okay, what happens when h gets smaller and smaller and actually becomes pretty much 0, okay, or the limit of this as h approaches 0. And we're going to find out next year that that is going to be called the derivative of the function. Okay, thank you.